From hurtling down cliffs at Red Bull Rampage to riding along the meandering paths of Bozeman's suburbs, bicycles experience a variety of loading scenarios. Shock-absorbing components called suspension help to mitigate the force exerted on the bicycle when in use. As everyone in our group is a serious mountain bike rider, we were interested in investigating the effects of both cyclic and static loading on a mountain bike shock's structural integrity. We narrowed our focus on the front shock of a Cannondale Lefty, a high-performance cross-country bike owned by our group member Philip. For reasons of simplicity, we modeled the suspension as a pressure vessel which elongates and shortens as forces from the ground and rider are applied to it, as seen in this schematic. We decided to analyze the component based off of two failure modes: fatigue and static crack failure. For both modes, 3 different levels of compression were considered: 0 cm, 3 cm, and 10 cm. We also analyzed the state of stress with no load, where the rider and bike are in freefall. The values for each scenario's respective load was calculated by combining the ideal gas law and the force equals pressure multiplied by area equation. For fatigue analysis, we calculated the number of trail rides the suspension could withstand before failure. A loading cycle was designed to represent a section of trail, starting with a drop and then followed by 8 rocks as seen in this figure. The points of 0 load represent the period of freefall after riding off the drop. The trail was composed of 10 consecutive repetitions, and we assumed that the rider took their bike on this trail once per day. Using these 4 loading scenarios, we created individual stress tensors for each case, solved for the apparent stress amplitudes and means using the von Mises method, and ultimately applied the modified Goodman theory to solve for the equivalent completely reversed loading stress amplitudes. The calculated apparent stress amplitudes, means, and equivalent completely reversed loading amplitudes for cycles A, B, and C, D can be seen in this table. We compared these results to the aluminum 6061 T6 stress lifetime fatigue curve, estimated a 1 billion cycles to failure limit, applied a safety factor of 10, and finally applied the Palmgren minor rule. This assessment determined that a shock under this specific loading scenario has a lifetime of 100 million cycles, or 273,690 years, roughly 1,348 times longer than bicycles have been used by humans. In other words, fatigue failure in a bicycle shock is of negligible concern. For the failure mode of static crack failure, 6 cases were first considered. For the 3 compressions, we determined the lateral crack failure length, where failure would be initiated by the combination of longitudinal stress and the bending moment, as well as cracks along the length of the shock for which failure would be initiated by the tangential stress component. The result of each scenario can be seen in this table. As shown, the linear elastic fracture mechanics criteria were only met for the case of maximum spring compression with a circumferential crack. The other cracks required for failure would not be able to fit on this shock, and thus did not apply to this situation. The result of a maximum crack length of 62.2 millimeters indicates that failure via crack propagation is highly unlikely, because if a shock has a 6.2 centimeter long crack in it, there's a good chance that the rider is already dead from the crash that caused the crack in the first place. All in all, riders can take solace in knowing that they can lead a cycling-intensive lifestyle without having to worry about their front shock failing, whether they're on the city streets or single track.